Hi, physics. Mr. Janowski here. This is Chapter 13, Homework 4, Problem 5. And we're going to do parts A through D because parts E and F are really just kind of doing the same thing again and again. But if I show you A through D, you should understand this well enough to figure out what's going on. So let's see what happens. We have a 1 kilogram object falls from rest out of the Kuiper belt, so way out there in the solar system, basically infinitely far away, towards the sun. So, A, what is the GPE of the object when it leaves the Kuiper belt, which is essentially infinitely far away? So let's do step 1, of course. Step 1 for part A. So what is the GPE of the object? GPE, and I'm going to call this GPE initial because this is going to be the first part of our problem, is equal to question mark joules, because it is energy, so its units will be joules. Part B, what is the object's GPE when it reaches the surface of the sun? So that'll be the end of our problem. GPE final is equal to question mark joules. Part C, using the conservation of energy and your results from parts A and B, what is the object's kinetic energy when it reaches the surface of the sun? Assume it doesn't burn up before then. Okay. So this thing's going to start in the Kuiper belt, it's going to crash in the sun, and we want to figure out what is its kinetic energy right before it crashes into the sun. So kinetic energy final is equal to question mark joules. And then the last part that we're going to worry about is what is the object's velocity at this point? So part D, V final is equal to question mark meters per second. Just barely able to squeeze that in there. All right, so where do we begin? Let's make a sketch of what's going on. So we'll do a part 1 here. So part 1, we're going to start way out here in the Kuiper belt. So here's our object 1, mass 1. It's going to eventually crash into the sun. So the sun's over here. So I'll call this big M, mass of sun. All right, so for part A, let's see, this is our initial, I'll tell you what, let's be consistent. This is our initial sketch. Maybe this will make the idea clear what's going on. That's our initial sketch. In our final sketch, what's happening? So here's the sun again. That's a terrible circle. Let me try that again. Not that the first one was great, but that was worse. Okay. That'll do for a circle. So there's the sun. At the end of our situation, where's our object? Well, it's just right at the surface of the sun. So it's gone this far. And now it's moving. It's going to have speed lines. So M1, M sun. And importantly, what distance is it when it's here? Well, when it's at the surface, it'll be the radius of the sun away from the center of the sun. So remember, when we're dealing with spheres, we always measure from the center. And just for completeness, let's go back to our initial sketch. What is our distance from the center of the sun? Yep. Sorry, not great at the Wacom tablet. What is our initial radius? Well, we're all the way out here in the Kuiper belt. That's really far away. Let's just round up to infinity. Let's say that we're infinity meters away. So we'll go with that. So now, part A. Pick a nice color. We want to figure out what is our initial GPE. So GPE initial is equal to, well, what's our formula for GPE? It is G mass 1 mass 2 over the distance. Let me call it distance initial because we're dealing with the initial situation. And I forgot something. Shame on me. I forgot the minus sign. Not actually going to matter for this one, but yeah, it should be there anyway. So what do we have? We have minus, and I could put in the numbers, but I know where this is going. So to save time, I'm not actually going to put in the numbers. I'm going with G1, M1, M2. M2 is the mass of the sun. And yeah, for distance 1, what is our initial distance? It's infinity, which means we're going to have something finite up here on the top. And then we're going to divide it by something infinite on the bottom. So what do you get when you divide anything finite by something infinite? You get 0. And for completeness, let's call it 0 joules. So technically, it would be a very small negative number, but it's so close to 0, let's just call it 0. So 0 joules is our answer for this part. So part B, make a little more room here. We need to figure out what is the object's GPE when it reaches the surface of the sun. All right, so let me get a nice shade of green here. So part B. So this is going to be our final. So let's go with GPE final is equal to minus, see, I remember this time, big G, mass 1, mass 2 over distance final. So our numbers are going to be minus 6.67 times 10 to the minus 11th, and I'm leaving off the units because the units are just a pain. Yeah, the units are newtons meters squared per kilogram squared. But I'm feeling lazy and I don't want to run out of room, so I'm leaving off the units for that one. Mass 1. What is the mass of this thing? The mass of this thing is 1 kilogram. And mass 2. We need the mass of the sun. So the mass of the sun, let me scroll back up here to see it. The mass of the sun is 1.99 times 10 to the 30th kilograms. So 1.99 times 10 to the 30th kilograms. Boop. And this will be divided by the distance final. Well, remember the distance final is this distance right here. It's actually the radius of the sun. So let's head back up to the chart. And the radius of the sun is 6.96 times 10 to the 8th meters. So here I've got to go with 6.96 times 10 to the 8th meters. All right. So you put all the numbers into the calculator. At this point, we're on homework 4, so you've done quite a few of these. Hopefully you're getting pretty good at the calculator. If not, reach out to me, send me an email or a Google chat or something like that, Google Hangouts chat, and I'll give you some extra tips on this. But if you do all that, the number you should end up with is minus 1.91 times 10 to the 11th joules. So put a box around it. Do step, Well, we solved for the right thing. We gave it, this should be final. We solved for the right thing. We gave it the right units. We got a negative number. Yeah, that makes sense. GP is always negative. And yeah, this looks good. So we're good with that. Now on to, back up to here, part C. So using the conservation of energy and your results from parts A and B, what is the object's kinetic energy when it reaches the surface of the sun? Assume that it doesn't burn up before then. Okay, so hopefully I can get my sketches in there. Let's pick a nice purple color. Oh, that's just lovely. Okay, so we have to use the law of conservation of energy. So this is one of our one with everything ideas. Sigma E initial plus sigma work external equals sigma E final. So right off the bat, yeah, we're not going to have any external work. This thing is just falling. There's no rockets. There's nothing like that. There's no friction. There's no air resistance. So now we go back and we look at our two sketches. So look at your initial sketch. So the questions we ask are, is it moving? Well, no, there's no speed lines behind that thing. This thing just fell out of the Kuiper belt. We just kind of dropped it from there. So there's no initial kinetic energy. Now for the GPE, what question should we ask? Well, it used to be, is it at a height greater than 0? Height doesn't really make sense in this context. You should say, is it at a distance less than infinity? I guess would be the equivalent thing. And in this case, it is not. It is at a distance of infinity, which means there's no GPE to worry about. And of course, there's no springs in this, so we're not worried about anything like that, which means sigma E initial Well, it turns out there is no initial energy. So we have 0 plus 0 on the left side, so we get that. And this is equal to the right side. So now let's look at our final sketch. So is it moving? Yes, it's moving. We have speed lines. So here are our speed lines. Boop. Which means we do have kinetic energy final. This is, after all, the thing we're trying to solve for. And then our question for GPE, is it at a distance less than infinity? It is at a distance less than infinity. So that means we're going to have to worry ourselves about the GPE final. So we have that. So what that means is we have 0 is equal to kinetic energy final plus GPE final. So the thing we're trying to solve for is GPE. So let's subtract, the thing we're trying to solve for is kinetic energy. So let's subtract GPE from both sides. So minus GPE final is equal to kinetic energy final. And we already know GPE final. That's the number we got for, let me make more room. I'm going up and down all over the place here. That's the number we got for part B. So what that means is minus 1.91 times 10 to the 11th joules is equal to kinetic energy final, which means kinetic energy final, the minus and the minus, is just going to give us 1.91 times 10 to the 11th. I can make a nicer one than that. Times 10 to the 11th joules. So put a box around it. Step, let's think of our answer. We solved for the right thing. We gave it the right units. This is energy. It's going to be in joules. We got a big number. Well, that makes sense. We're dealing with astronomical things. And it's positive, which is good because kinetic energy can only be 0 or positive. So we should end up with a positive number in this case. So that looks pretty good. Now what color should we go with? Let's find an orange. So the last thing, orange, it's going to look a little brown. The last thing we're trying to figure out is what is the object's velocity at this point? So do we have a way of figuring out the object's velocity if we know it's kinetic energy? Yeah, of course we do. So we know that kinetic energy final, in this case, just to be particular, is equal to 1/2 times the mass of the object. We're dealing with the object, not the mass of the sun, times its final velocity squared. So we've just got to do the algebra here that solves for velocity final. So first, multiply both sides by 2. So that'll give us 2ke final on the left. That would be equal to mv final squared. Then divide both sides by m. So that will give us an m in the denominator over here, and that would kill off the m on the right side. So that's equal to this. And now let's take the square root of both sides. And when I do that, that'll go away. And I have this, which means v final is going to be equal to big square root 2 times the kinetic energy final, 1.91 times 10 to the 11th joules. All of this divided by the mass. So what was the mass of this thing? The mass of this thing was 1.00 kilograms. I didn't get super creative with the mass of this thing. So you do all that in the calculator. You have to do 2 times this number divided by this number, and then hit enter and get the whole thing. And then you take the square root of that. And when you take the square root of that, what number do you get? You should get something like 6.18 times 10 to the 5th meters per second. So put a box around it, do a step, does this make sense? We solved for the right thing, we gave it the right units, and we got a big number. So 6.18 times 10 to the 5th is the same as 618, move the decimal point, 1, 2, 3, 4, 5, 618,000 meters per second. So yeah, that's pretty fast. Bloody cheetah. That's 1.2 million miles per hour. So yeah, it's pretty fast. But again, we're dealing with astronomical things. This thing fell from basically infinitely far away into the sun. So it had a whole lot of time to gain a lot of speed, which means, yeah, we are expecting a big number here. So it looks good. We're happy with that. So hopefully that made sense and you found it helpful.